Okay.
I guess there is also a introduction to basically we have chapter 2 Monte Carlo integration, where we're talking about Monte Carlo integration, which is a way to numerically approximate integrals because they don't have analytic solutions. And there are some other algorithms, like more standard numerical integration techniques you learned probably in the math class, like trapezoid integration, but they have curse of dimensionality problem, and for rendering we have very high dimensionality, so we need to use something different, and the Monte Carlo integration does not have this problem.
Could you explain like what you mean by high dimension here in case of rendering?
Okay. Well, this week.
What? Sorry, what you said?
I said, could you explain what you mean by high dimensional problem in this case?
Oh, high dimension. So because we can have a lot of different light sources, for example. This we need to take into account of all of those. And so it's not just 3 dimension. We have a lot more, and every time, for example, we add a light source, we basically just add new dimensionality for the integration. Does that answer your question?
Yes, I was like thinking in terms of functions, like right, like if we have x, y, z, w, whatever, right? Like, I was like wondering. I thought that's what the higher dimension means. That in case of in case of these kind of path tracing rendering, we have many more. We have a lot of dimensions over which we have to do integral.
It doesn't mean like physical dimensions. It means the function input. Yeah.
So I guess also you have to worry about like surface information, because for every like bounce you're doing, so you'd have to like integrate over all possible like roughnesses or whatever, and then all possible like occlusion levels and all that.
Right, that makes sense. Thank you.
Which is very helpful.
It's
and then around any value direct positioned around
the plane.
Yeah, in our just maintain
because of the way the illumination, right? Is that it all meshes together, I guess. Somehow.
This chapter talks about just some basic information of Monte Carlo integration, which you probably already know a lot of it, but we will do some review so everyone will be on the same page. So firstly, the chapter starts with some probability review. And it's just brush through those concepts. So if you don't find them enough, then probably go into some other more deep review of probability. Here, just those concepts like random variable x. just choose by some random process. Can be either discrete or continuous. Apply a function. We can apply a function to a random variable, which is like we map this function to each individual sample of this random variable, and the result is a new random variable. And two random variables are independent if the probability of one does not affect the probability of another. Yeah, something like this. The joint probability is just a product of the probability. But a lot of the cases, random variables are dependent, and then we have something like this, which is the conditional probability. Like, for example, in here, when we sample light source, when we're doing some important sampling for the light source, then definitely the probability of choosing which light source depend on a lot of other probability. And then there is the so-called canonical uniform random variable, which we write at, I don't know what this is. I? Can someone tell me what this is? But anyway, this is a uniform random variable from the
Did Leslie just drop for everyone else?
I think so, yeah.
Well, we will eagerly wait his return.
My Discord just crashed.
Oh.
I think I'll have to restart the stream.
I believe the letter is Z, like XI.
Yeah, I had looked it up at Wikipedia.
But is it pronounced Xi or Z? Is it?
I always pronounce it Z, but I don't know if that's correct. I remember we talked about this before, but I forgot what our conclusion was.
No one knows. All right.
Well, I sent a picture of it in the chat, so
Yeah.
you can decide for themselves.
I'm seeing Xi on Wikipedia.
Xi?
Fox. So that might be okay. It's a consonant, it seems. So that's like X.
Oh, it says it's pronounced Psy or Shy in English.
Okay, so random variable Xi. I prefer curly E. Xi. 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 Say whatever you want, as long as we all understand what you mean.
Yeah. All right. So for lighting applications, we might want to define the probability of sampling illumination from each light based on the power. And then there is CDF, the cumulative distribution function.
I started.
Which is the probability of value from the variables distribution is less than or equal to some value. So for the discrete case, then we just add all the probabilities that is less than or equal to, and for the continuous, we need to do an integration of the PDF to get CDF. I guess they introduce PDF later.
I always get
And-
PDF and CDF mixed together.
The CDF is integration of PDF from like negative infinity to whatever.
Yeah, if you graph them, the CDF like approaches one as the like it's like monotonically increasing as opposed as x increases.
Yeah. CDF is really useful for stuff like, remember we talked about inverse CDF to just as a way to combine different PDFs together. And also expected value is it's a function defined as an average value of the function over some distribution of value. So if we have an expectation of cosine pi between 0 and pi, we can make it an integral. And the PDF, we just have a uniform distribution, and so we get 1 over pi. We can think it as a normalization factor, and then we just get 0 at the end, which is expected because cosine kind of oscillate between 1 and -1. So the average is 0. And we have some probabilities like those, which are often called like expectation is linear, so we can do this kind of stuff. So for Monte Carlo estimator, we can finally define it for a 1D integral like this, and give a supplement of independent uniform random variable. And the Monte Carlo estimator says the expected value of the estimator is this. We basically take discrete samples from this function. and then normalize it by the PDF, which in this case is always divided by n. And we can show the expectation of this function. We get back the integral. So that means we can do this stuff. And if we have enough samples, we get back our integral on average. And for multiple dimensions, we just take more independent samples from each dimension. And the estimator is applied in the same way. So I guess another way to think about it is the dimensionality of Monte Carlo integration is exactly the number of independent sample we
I am
take.
recording.
So every time you call rand, you increase dimensionality by 1. Leaving direction by so. And we get back the same result for multidimensional too. And for estimating error in Monte Carlo estimation, we need a concept of variance. So the variance of an estimator f is defined by this equation. And
Rip.
They didn't want him to tell us about the variance.
and it crash again.
Yeah.
Does it crash for you often, or
No.
do you not use Discord enough and stream it enough to have a sample size?
Yeah.
It's really obnoxious that it crashes. But we're back.
Yeah, I don't know what's going on. So then we can get this more familiar equation for variance because of this property. So variance of expected value is the square minus the square of expected value. And if the estimator is a sum of independent random variables, then the variance of the sum is the sum of the individual random variables variance. I feel like this book just like breeze through a lot of those properties without actually talking about them. like this and this. But I guess that's why they say it's just a quick overview of what's going on. I know those stuff, and I still feel like sometimes I need to think harder. But anyway, from this equation, we can say that the variance decreased linearly with the number of samples n. And variance is the squared error, and so the error of Monte Carlo estimate therefore goes down the rate of O(n) of -1/2. So one good thing about this is that the error, this rate does not depend on the dimensionality. So compared to standard techniques. So even though Monte Carlo integration perform pretty bad in one dimension, it gets better and better with higher dimensions. And also this characteristics is apparent when watching a progressive rendering of the scene, which is to reduce error, we need more and more samples. We need one sample, and then need two sample, and need 4 sample to reduce the error in the same amount.
Okay.
I guess there is also a so the linear decrease of variance also make it easy to compare different Monte Carlo estimators, because if the second has half of the variance of the first but takes 3 times as longer, then the first is better, because with the first, then we can just take double the samples. So this concept can be encapsulated into so-called efficiency of an estimator. Where is the inverse of variance times the runtime. Because we want runtime to be small and inverse to be small. And also there are some estimators that are biased, so they will never, their expected value is already not equal to the true value of the integral. Yeah, so there are some bias. Yeah, they may still be desirable if they are a lot quicker.
Okay, well, shape like that.
So here is an example that the mean value of uniform distribution over interval of 0 to 1, we could use this, which we or one could use this. The first estimator is unbiased but has variance, has a larger variance. The second estimator's expected value is biased. But yeah, the variance is much better. And also the bias go to 0. Yeah, this is called consistent, which is it has bias, but the bias goes to 0 when we have larger and larger sample. And most of the Monte Carlo estimator used in PBRT are unbiased, but some are biased. And another concept called mean squared error, which defined as expectation of the squared difference of estimator and the true value. I feel like I learned this in physics class before, but I forget all of it. And for unbiased estimator, this is equal to the variance. Otherwise it's the sum of the variance and the square bias. Because for variance here is the expectation, not the true integral. So it is possible to work on variance and the mean squared error of some simple estimator in closed form, but for most of ones interested in rendering, it's not even possible. But it is still be able to quantify those values, and then we can have a sampled variance. Can be used to compute with a set of independent random variables. So we can have a sampled mean, and then the sampled variance is pretty trivial to calculate, and then we divide by n-1 instead of n. This is called Bessel's correction to ensure that the sample variance is an unbiased estimate of the variance. And the sample variance is an estimate of variance, so it has a variance itself.
Variant of the variant.
Variance. Yeah, variant makes me think about like what we have, say, in language like C++, right?
Like standard variant.
Standard. Oh, I'm confused. It should be standard var. No, wait, what? Oh, yeah. I'm thinking about this. If you talk about variant, I'll also call like those tagged union type in other language variant. I think because of ML call it variant, so yeah.
I mean, all this stuff about error is just quantifying how wrong your guesses are. And there's multiple ways to
Yeah.
do that, and different and better ways to get a sense of how wrong you are, or how wrong a estimator is, and how to. And if you know how wrong an estimator is, it's easier to find out, or you can figure out how good it is.
Yeah, I feel like it's useful to compare different estimators. Otherwise, it's just a number.
Yeah.
Also, I guess it's useful to compute the image error with the reference image. All right, we are done with this section, even though I feel like I still need to revisit some of those stuff.
Agreed.
Yeah, but it's not that too difficult, at least for me, because I still remember most of those concepts.
Yeah, I was drilled on this in my university statistics class, and I was eternally annoyed that the sample counts were always so low. When I say sample counts, all the problems we worked on were either completely theoretical or very much here's 25 samples, and in the realm of graphics and like ray tracing stuff, you get 25 million samples. So you get much different perspective on things, in the terms of scale.
Yeah, but also you always deal with those kind of stuff in math class because you have. But well, at least in my math class, maybe it's because I took them in applied math department. They still have a lot of stuff in MATLAB. I hate that, but at least they can have larger scale problems.
Yeah, all of mine was engineering department based, and I think the early part of the class had the small sample counts, like here's 25 numbers, compute various properties about it. The second and third test had way more. Here is the formula for a specific distribution, and looking at the yeah, it was a whole lot more theoretical than individual, real numbered based. I don't know how to describe it.
Yeah, but also you just can't get people to solve this kind of problems in an exam, right?
That's very
They
true.
can only be projects.
I concur to that. Well, I think we can end it here. Pick it up another 2 weeks.
Yeah, we can end it here.
Okay, I'll end recording. recording.